Good morning. So we've been working with solving different types of equations. We've gone through solving linear equations in form that when we start working to solve them, they become linear. We continued then looking at quadratic equations in form and all the different methods that we can solve quadratic equations. Factoring is usually the easiest if it's possible. It's not always possible to factor. But then we looked at the square root method if it was in a certain form, or putting it in that form by using completing the square. We derived the quadratic formula by completing the square method. And now we're looking at complex numbers. And so we got pretty far in complex numbers at the end of the class period. And we're going to continue with complex numbers today and then solving more different types of equations with radicals in them. So let me share my screen with you and we'll get going. So we were looking at performing different operations while we were working with complex numbers, adding, subtracting, multiplying. We looked at the conjugate of a complex number that was just changing the sign between the real part and the imaginary part. So let's look at the following example, and it says find the product of 6 minus 9i and its conjugate. And so the conjugate again of 6 minus 9i if I put that bar over it, that represents the conjugate. So this right here is equal to 6 plus 9i. And so we want to look at multiplying 6 minus 9i times its conjugate, 6 plus 9i. So looking at this, if we distribute, we have 6 times 6 is 36. 6 times 9i, that gives us plus 54i. Negative 9i times 6, this is minus 54i. And 9i times negative 9i, so that's negative 81i squared. So recall I was equal to this, by definition, the square root of negative 1. And if we square both sides, we can say I squared is equal to negative 1. And so we want to rewrite this. I'm running out of room on there. So notice that 54i minus 54i cancels. And so we have 36 minus 81i squared. But again, I squared is negative 1. So really here this is equal to 36 plus, because minus a negative 81 is plus 81. And so summing this, we get 117. So looking at this, we want to write complex numbers in standard form. So to express the quotient of two complex numbers in standard form, multiply the numerator and denominator by the conjugate of the denominator. So notice that this example above, we multiplied a complex number by its conjugate and we got back a real number. And so that's always going to happen. And so that's why we're going to want to clear the imaginary number in the denominator. We can multiply both the numerator and denominator by the conjugate. So why does multiplying the numerator denominator by the conjugate of the denominator help us write the quotient of two complex numbers into standard form? And what does it do to the denominator? Well, I kind of just answered that question. Multiplying the conjugate, basically when we're multiplying by the conjugate to the numerator and denominator, we're multiplying by this fancy one, right? And multiplying by the conjugate of a complex number, that gives us back a real number. So that kind of undoes the imaginary part. And so over here, let's look at, I'm going to do it on the side. Look at 6 minus I, all divided by 4 plus 3i. Okay, so this is not in standard form of a complex number. We want to divide, so we're going to multiply this by a fancy one. And that fancy one, again, is going to be the conjugate of the denominator. And so that case, we have 4 minus 3i. or minus 3i. So for the numerator, we want to distribute. So 6 times 4, that's going to give us 24. 6 times a negative 3i, that gives us minus 18i. Negative I times 4, so minus 4i. And negative I times negative 3i. So that's positive 3i squared, but I squared again is negative 1. So that will give us a minus 3 there. All over. So you actually want to get in the habit, if we have the conjugate here, multiplying by conjugates, remember a minus b all times a plus b. This is always a squared minus b squared. And we're going to use that a lot, that fact of multiplying two numbers by conjugates. We're going to use this to help us. And so we don't have to FOIL each time. Just one sec. So let's just do that. So if we square our a value, and I'm going to just write this down. We have 4 plus 3i, right? If I square this 4, that gives us 16 minus, and then if I square my b value, 3i times 3i. Again, that's 9i squared, but the I squared is a negative 1, so this is minus 9. Okay, so let's combine like terms in our numerator. And so 24 minus 3, that gives us 21. And then negative 18i minus 4i, that gives us negative 22i. All over 16 minus a negative, so 16 plus 9, which is 25. This is not in standard form. So if you went in and plugged this into the computer, it's going to probably say you have the right answer, but not in the correct form. So remember, it's the real part plus the imaginary part. So when you have a fraction, we want to break it down as two separate fractions. So we can rewrite this as 21 over 25 minus 22 over 25 I. And so there we have the division of two complex numbers. So any questions on that one? Okay, so the next example, we have negative 4 plus 5i all over 6i. Notice that there's not two terms in the denominator. And so we really don't have to multiply by the conjugate of the real plus the imaginary part, because it's just the imaginary part. So I can technically, or another thing that you can think of is 6i, if you want to think of it, is the same thing as 0 plus 6i. So the real part is 0 there. We can multiply both sides by, if you want to think of it as a conjugate, that would be a negative 0 minus 6i. So the conjugate we can denote with that bar on top, that horizontal line. And so we can do this. We can multiply both sides by, not both sides, both the numerator and denominator by negative 6i. Okay, so we need to distribute on top. So we have a negative 4 times a negative 6i. That's going to give us a 24i. And then we have 5i times negative 6i. So that's negative 30i squared. The I squared again is negative 1. So negative 30 times negative 1, we have a plus 30. All divided by 6i times negative 6i. That's negative 36i squared, which is positive 36. So again, this is not quite in standard form. We want to rewrite it. Usually we rewrite it with a real part first, and let's rewrite it as two separate fractions. So 30 over 36 plus 24 over 36 I, and pull the I out. So we're not quite done because I noticed that the fractions have common factors, and 30 and 36 both have a oh my gosh, 6 in common. 6 goes into 35 times, and 6 goes into 36 6 times. Plus 24 and 36, those two also have a 6 in common. 6 goes into, actually, do they have more than 6? Looks like they have 12 in common. 12 is the biggest factor. So 12 goes into 24 twice, and 12 goes into 36 3 times. I. Okay, so if we're dividing two, or if we have a fraction of a complex number divided by a complex number, we can rewrite it in standard form by multiplying through the numerator and denominator by the conjugate of that denominator. Okay, so let's look at using some of our rules with conjugates, and the following states the conjugate of a complex number is the complex number itself. So if I look at the conjugate of the conjugate, I get the original complex number of z. And we can show that that's true. A lot of mathematics, and the further you get into it, you're proving things and showing why a statement is true. And so let's say that z was equal to the complex number of a plus bi. And by definition, the conjugate of z, written as z bar, is equal to a minus bi. Well, if I take the conjugate of a minus bi, that's again just changing the sign between the real and the imaginary part. This gives me a plus bi, which is equal to our original z value complex number. So another statement. So this states that the conjugate of the sum of two complex numbers equals the sum of their conjugates. So instead of first summing your two complex numbers and then taking your conjugate, this is saying that we could take the conjugate of the first number plus the conjugate of the second number. Okay, so again, let's show that that is true. So let's just define generically. Let's say z again is a plus bi. And let's define w. How about c plus di? And we want to show sum of two complex numbers and their conjugate is equal to the conjugate of the first plus the conjugate of the second. So when we're trying to show or prove something is true, usually you just work on one side of the equation and you're manipulating that one side to look like the other side. And so you choose one side to work with. And so let's work with the left-hand side. So if you've taken trigonometry, you were showing, and part of that course is showing that identities hold true, and you chose what side of the equation you wanted to work with. Usually it was the more complicated side, and you manipulated it to fall out and look like the other side. So same kind of idea here. So let's rewrite this so that z plus w and that conjugate. Let's define it again. So that was saying take the real part, which is a plus bi. I'm sorry, take the complex number, first one, a plus bi, plus the second number, which was c plus di. And we're going to look at the conjugate of that sum. So let's rewrite this. Let's rewrite it where we have the real parts next to each other and the imaginary parts next to each other. And so a and c are the real parts. And so let's rewrite that as a plus c. And then plus bi plus di. We're taking the conjugate of that. let's factor out the I from the imaginary parts. And so we get A plus C plus B plus D in parentheses I, and the bar is still over this. So technically, I'm just going to put, and it doesn't matter, it's the same thing. I'm just going to put parentheses around my real part. And so notice here, this, if I take the conjugate now, that would be just changing the sign between the real part and the imaginary part. So that's just going to be changing that sign to a minus. So we still have the parentheses A plus C minus B plus D, I. I don't need the parentheses around the real part, so I'm just going to rewrite it, A plus C. And I'm going to distribute the negative I to each term. So negative I times B, that's going to give me a minus BI. And a negative I times D, that's a minus DI. Well, I'm trying to show this is equal to the conjugate of Z plus the conjugate of W. So let's rewrite this. So I have A minus BI, I'm just rewriting the order. And then I have plus C minus DI. But notice that this A minus BI, this is what, it's the conjugate of Z, because Z is A plus BI. So this is Z bar plus, same idea. If I look at C minus DI, well, W is defined as C plus DI. And so that's just the conjugate of W, which I could write with W with a bar over it. And so we showed that the sum of two complex numbers and taking their conjugate is the same thing as taking the conjugate of one complex number plus the conjugate of the other complex number. So it's kind of fun. So a lot of times you'll finish a proof showing something is true and you put a little square under there, and that just is a notation in mathematics that the proof is done. You've shown it. You showed what you wanted to show. Okay, so let's go to the next statement about complex numbers. And what this one states now is the conjugate of the product of two complex numbers is equal to the product of their conjugates. So if I take two complex numbers, multiply them together and take their conjugate, this is saying that this is the same thing as taking the conjugate of the first times taking the conjugate of the second. Okay. So again, you should be able to go through and prove that this is a true statement. Okay, so again, we want to show that if I multiply two complex numbers together and take their conjugate, this would be the same thing as first taking the conjugate of the first times the conjugate of the second. So my Z's I make, just because I haven't stated this in the past and I've had students come up and ask me about it, what's that symbol? My Z's, I have this little bar through it, and that's just helpful so that you know that that's a Z versus a 2 when I'm writing. Okay, so I'm going to define Z to be the complex number A plus BI. And let W be the conjugate or the complex number C plus DI. So if I'm looking at the multiplication and then taking the conjugate, let's just rewrite it. Z we said was A plus BI. all times W, which is C plus DI. And we're going to put that bar over that product. So you're going to want to distribute and then combine like terms if possible. So distributing A times C, we get AC. I know that's a real number. A times DI. So this is ADI. That's an imaginary number. BI times C. So this is BCI. Plus, well, BI times DI. So that's BDI squared, which is the same thing as negative BD. I didn't realize that was below. So let me just get rid of that. So let's rewrite it so that the imaginary parts are together and the real parts are together. And let's pull out the I. So right here, I'm going to pull out I, and I'm going to rewrite the real parts together. So I have AC minus BD. And then I have plus AD plus BC times I. And I haven't taken the conjugate yet, so I still should have that bar over this. So I'm just going to put parentheses around my real part. And so let's rewrite this without that bar. Let's take the conjugate of this. And again, the conjugate is just changing the sign between the real and the imaginary. So I'm bringing down my real part, this AC minus BD. I'm changing the sign in between, so minus, and then I have AD plus BCI. So I'm going to distribute negative I to both terms. So we have AC minus BD. Distributing the negative I have minus ADI minus BCI. Okay, so I want to get it to look like the conjugate of Z. So A minus BI. I'm thinking that I want to regroup things. Actually, did I do something wrong? Yeah. When I brought down this should have been BD. Okay, so let me see, what can I group together? So let's group AC minus BCI together. So I'm just going to rewrite those next to each other, AC minus BCI. And then let's group negative BD minus ADI together. So minus BD minus ADI. So I'm not seeing it come out like I wanting it to, but let me just, and sometimes you're just like, I have to play with it and see, and hopefully it comes out, or you might have to go back and manipulate it. And so I noticed here, the first two terms, let's kind of think about this with grouping. And so notice that I can factor out a C. And so if I factor out a C, let's look at that, that would give me A minus BI all times C. And then I notice over here, this has a negative and a D in common. So let's pull out a minus di. I'm going to put it on the left for some reason. And if I pull that out, I'm left with b minus ai. And I'm not seeing it quite yet. So let me just pause that. I pause for a second and look at it. Okay, so I'm kind of just going through what I'm seeing and talking it through. So first of all, coming back here to this piece, we pulled out a negative, but we're only pulling out a b. No, we're pulling out a d. So if we pulled out a negative, that would leave me with b for the first term. This should be plus ai all times d. Okay, so I know what I'm trying to get. I know that I'm trying to get my result to be the conjugate of z times the conjugate of w. And so what's inside my bracket is almost identical to, well, the first one, a minus bi, that is identical to the conjugate of z. We can manipulate this second parentheses to look like the first, or bracket, look like the first bracket by thinking about it as factoring out, like I was doing before, an I. And we would have to think about what would get us back to the original. So let me get myself some more room. So let me maybe do this over here. So if we have minus, just looking at this, b plus ai all times d. And let's say that we pulled out an I. Can we do that? So I'm thinking to myself, what could I multiply b by? Now, that's not going to work. Pull out an I. If I rewrite this as bi, let's do that, plus just a. And I'm thinking to myself, what would I multiply along with the d to make this a positive b up here? Well, if I do I times I, that is going to give me an I squared. So that's going to be a minus in here. Right? Because I squared is -1 with a negative in front of my b, that would get me my positive b back here. And then if I pulled out an I, or if I'm thinking about multiplying by an I here, this would give me the correct thing in this piece. And so I'm going to go back and I'm going to rewrite this with this. And so we did that. We manipulated what was in the brackets to be the same. So a minus bi all times c minus, the other thing I want to do right here is let's rewrite the order here. So this is minus, I can rewrite the order inside the bracket as a minus bi all times di. So a minus bi all times di. So notice again, what's inside the bracket is the same. So we can factor that out of both of those terms. So we're pulling out this a minus bi. And if we pull it out of this first grouping, notice that you're left with just a c. Minus, and if we pull out that a minus di from the second grouping, we're just left with this di. There we go. And so a minus bi, well, that's the conjugate of z. So we're going to rewrite that as z bar. And c minus di, that's just the conjugate of w. So times the conjugate of w, which is what we were trying to show. So that one was a little more difficult in the fact that I had to kind of manipulate it and looking at what I was trying to get a result of to fall out like that. Okay, so let's look at an example. We're given that z is equal to 3 plus 5i, and we're given w is equal to negative 2 minus 4i, and we want to find the following. Okay, I don't know why that mark is up there. I don't like it, but it won't erase. Okay, so let's look at what if about z divided by w bar. Well, we can write this out. This is saying I'm looking at 3 plus 5i, all divided by negative 2 minus 4i, and we're going to take the conjugate of that. So this is 3 plus 5i all over negative 2 plus 4i. So division, complex numbers, get rid of the complex number in the denominator. We can multiply through by the conjugate. And so the conjugate of our denominator, just change the sign between the real and the imaginary part, we get negative 2 minus 4i. So we want to distribute in our numerator. We get negative 6. Distributing that 3, we get negative 6 minus 12i. Distributing our 5i, we get negative 10i. And then 5i times negative 4i, that's negative 20i squared, which is really plus 20. All over, and so square the first number. So negative 2 quantity squared is 4, minus, let's square the second term. So 4i times 4i is negative 16. So in the numerator, let's combine our real parts and our imaginary parts. So negative 66 plus 20 is positive 14. Negative 12i minus 10i, so minus 22i. All over 4 plus 16, which is 20. So when we rewrite this as two separate fractions, we have 14 over 20 minus 22 over 20i. And then we want to reduce our fractions. So 14 and 20 have a 2 in common, so that would leave us with 7/10. Minus 22 and 20 have a 2 in common, and that will leave us with 11/10. And so now it's in standard form of a complex number. Okay, so let's look at one other piece in this section, which talks about taking I and raising it to some power, any power. Well, that could get really tedious, but if you notice, let's look at the following. By definition, right, I is equal to square root of negative 1. Let's say I want to square I. Well, we saw that I squared, squaring both sides, we would get back negative 1. So let's continue on this process of raising it one exponent one more each time. So let's look at I cubed. Well, let's use the facts that we know above. We know that I cubed is the same thing as I squared times I. So we'll be using this rule a lot, rules of exponents. Same base, remember, you add your exponents. And so if I wanted an I cubed, I can rewrite it as I squared times I, adding the 2 and the 1 gives me that cubed. And so let's just rewrite this a little bit. And so I squared, remember, is -1 times I, or negative I. And I'm going to just put these over here so that we can look at what's going on. So let's look at I to the 4th now. So I to the 4th I can break down as I cubed times I, or I squared times I squared. It doesn't matter, just choose one of them. Let's do I squared times I. Well, I squared, remember, is -1 times -1. This would give us +1. If we continue and we did I to the 5th power, well, we can say that's the same thing as I to the 4th times I. Well, right above, right, we found out I to the 4th was 1. So we could rewrite this as 1 times I. So I to the 5th is equal to I, which notice is the same thing as I to the 1st. And so if we look at it, I to the 6th, well, I to the 5th times I. Well, I to the 5th is I times I is -1. And so you get -1 here. And so there's a rule, because we know it's going to be repeating every 4th I. There's a rule that says if you have I to the nth power, this is the same thing as I to the R, where R is equal to the remainder of n divided by 4. Okay, so that's helpful, because for some reason, if we wanted to look at I to the, let's say, 121st power, I wouldn't want to go through what we were just doing 121 times. And so I would use this rule. I would look at 4 going into 121. Well, 4 goes into 12 evenly 3 times. And then 4 does not go into 1. It goes in 0 times. And so I have a remainder here is 1. So I know that I to the 121st power is the same thing as I to the 1st power, which is I. So I'll pull up another example, maybe one that's on that note page. Okay, so let's look at the following, evaluating the powers of I. First one is I to the 23rd power. So again, I'm going to look at 4 going into 23 and see what my remainder is. Well, I know 4 goes into 23 5 times, which is 20, and my remainder is 3. And so I know then that I to the 23rd power is the same thing as I to the 3rd power. And then if you don't remember what I cubed is, we can break it down to things that you know, which is I squared times I. I squared is -1, so -I. Be careful here. On part B, we have -I to the 67th. It's the I part that's only raised to the 67th power.
Can I ask what made you in part A divide it by 4?
Because I know that, because I know that it's going to be repeating every 4th power. So the power of IA repeats every 4th power.
Okay.
And so we can, if it's the exponent is higher than 4, then divide that by 4 and use the remainder as the exponent, and it will be the equivalent. Does that make sense? And so same idea here, negative I to the 67th. Well, I don't want 67 is higher than the power of 4, so I want to look at the remainder of 4 into 67. Be careful because of this negative out front. That negative is not being affected by that 67th power. So this is really negative I to the 67th. And so I want to look at how many times 4 goes into 67. So okay, 4 goes into 6 once. Subtract, so I get 2, bring down my 7. 4 goes into 27 6 times. So 4 times 6 is 24. Looks like I have a remainder of 3 again. So this is equal to the same thing as negative of I cubed. And I cubed, we know, is the same thing as negative I. So negative of negative I, which is equal to just I. So the next one, part C, I to the negative 24th power. That's a negative exponent. Let's first rewrite that negative exponent as a positive exponent. And we can do that. Recall, a negative exponent just changes. If it's in the numerator, it goes down to the denominator. If it's the denominator, it goes up into the numerator. And so I can rewrite this here as 1 over I to the 24th power. So we'll figure out what I to the 24th power is. So we want to look at 4 going into 24, which it goes in evenly 6 times. So my remainder here is 0. So this is going to be the same thing as 1 over I to the 0 power. And recall, numbers raised to the 0 power other than 0 is equal to 1. And so I to the 0 power is 1. We get 1 over 1, which is 1. So really the last thing I just kind of want to go over is now that when we are solving quadratic equations, remember we could have gotten a negative underneath the radical. We had talked about the discriminant before, which was b squared minus 4ac. Oops. I want to extend this way. So our discriminant again was b squared minus 4ac. Quadratic equation, again, if we had something in the form of ax squared plus bx plus c equals 0, we could say that x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And so the discriminant was that portion, what was underneath the radical. And if we figured out what that number is, then we would know if we had what type of solution we had and how many. So in the complex number system, consider the quadratic equation ax squared plus bx plus c equals 0 with real coefficients. If b squared minus 4ac, that discriminant, is greater than 0, then the equation has 2 unequal real solutions. Right? If we have a positive number underneath this radical, we're going to take negative b plus that positive number, or that whatever that square root is, and then negative b minus whatever that square root is, and then divide by 2a. So that's 2 different unique real solutions. If our value was equal to 0, Well, if I have the square root of 0, that's 0. So that's negative b in the numerator plus 0 is the same thing as negative b minus 0. And so we're going to have one solution, but it's repeating itself. And we'll see that that's kind of important when we get into graphing. So the equation has a repeated real solution. We call it a double root, or has multiplicity of 2. We'll talk about multiplicity later, though. And then if what we had underneath the radical was negative, well, we saw that the square root of -1 was just an imaginary number I. So if this is less than 0, we have negative b plus an imaginary number and negative b minus an imaginary number on top. And so that's giving me 2 complex solutions that are not real. And the complex solutions are actually conjugates of one another, right? A negative b plus some value of ci. So let's say that the square root of b squared minus 4ac, let's say that this was equal to ci over 2a. And then we would have that negative b minus ci all over 2a because of the plus or minus here. So those are conjugates of one another. So the next example, I'm not going to go through, we'll see some of these examples in the next section. So now you can have a quadratic equation that's not factorable. Quadratic equation that's not factorable. You would use the square root or the quadratic formula. I need to slow down and figure out what the solutions are. Okay, so that is finishing off the complex numbers, operations of complex numbers and imaginary numbers. So I'm going to stop here and we'll go into the next section.